Hey guys, welcome to another video. Today we're going to go over significant digits and formula mass. So take a second, pause this video, pull out these four things. One thing that I didn't mention that you might want to pull out as well is the polyatomic ion sheet, because we might have some formulas we're dealing with today that have polyatomic ions in them. Calculator. This is a very mathy unit, math-based unit, where we're going to really do a lot of calculations. So please, from now on, start bringing your calculator to class because it's going to be really important that you have that. Okay, so with that, I'm actually going to first start off by getting out of the screen because my slides they show everything and not the animations. And since I'm doing a presentation like this, it doesn't quite do the whole effect unless I just have part of the slides up. So what I'm doing for you right now is off to the side, I'm writing down 3 different measurements. And I want you to just take a second, look at these, and identify what are the similarities and differences between these 3 measurements. Some of you might say that they all have the same units. Centimeters, centimeters, and centimeters right here. You'll also see that they all are technically the same number. This one's 8, this one's 8, this one's 8. The only difference that you can probably see on the screen is how many zeros we are dealing with. So we have, in this example right here, this one only has one number right here, meaning that whatever instrument or measuring stick that we used to measure these 8 centimeters, it wasn't very accurate. So we weren't able to be really detailed or specific on how long this measurement was. Now, if you look at this one over here, 8.0, this 0.0 adds another digit, and this digit is significant because our measurement, or our ruler, was accurate enough for us to measure to the tens place. So let me write this out real quick. This one only went to the ones place. This one went to the tens place. We will find out that this tens place one, since it has more numbers, this one is a more accurate measurement than this one on the left. Now this bottom one right here is accurate up until the hundredths place, meaning that whatever instrument we used to measure this was the most accurate measurement by far because we were able to get to such a tiny number. So let's go back to our presentation. What you're going to see with these is, depending on how many digits you have, tells you how accurate your measurement is. And we've done measurements in the past. We've looked at milliliters, we've looked at graduated cylinders, seeing how much water is in these, but we haven't really done with measurements other than saying it has this much water in it, or it's this long. This unit, we are going to be taking numbers and multiplying and subtracting them and doing all sorts of math with them. And so we're going to have to talk about an important topic called significant figures, or significant digits. It kind of goes back and forth on which way you want to say it. Scientists, they over time just shorten it to say SigFigs. So if you hear me say SigFigs, I'm just meaning significant digits. And I have a meme down here just says, brace yourselves, here comes significant figures, because this is going to haunt a lot of you guys for those who want to go into the medical field or anything like that in the future, because this is really important. And even in college, people still get tripped up in this. So, in the last problem, we had 8s and 0s, and we can tell which ones were significant or not. Well, oftentimes when you're dealing with data, it's not as easily cleared out to what the significant digits are. So I have 4 rules. All non-zeros are significant. I am going to go through this really fast so I have time later in the video to do other things. So pause it if you need a second, but all non-zeros are significant. Non-zeros is referring to anything that is not a zero, so 1s, 2s, so on and so forth. You'll see I have an example, 873. Now, how many significant digits do you think are in that? Well, the 8 is a non-zero, so that's 1 sig fig. This 7 is also a non-zero, and this 3, so we're going to say this has 1, 2, 3. Each one of those counts as towards our significant figures. This thing we're going to say has 3 sig figs. Now, rule 2. Zeros trapped between non-zeros are significant. What I mean by trapped is a zero between other non-zeros. So I have an example over here, 607. Let's find out how many sig figs are in this one. 6 and 7 are non-zeros, and so based on rule number 1, we do know that these are significant. But this 0 right here is actually significant as well because rule 2, it's trapped between two non-zeros, so it is significant. Now, rules 1 and 2, those are pretty easy to get for most students. 3 is where it especially gets tripped up a lot. Trailing zeros, meaning any 0 that follows a non-zero, are not significant unless there is a decimal point. So to help with this example, I have 3, 250, 250.0. So let's look at this far left-hand one right here. This 2 and this 5, these are non-zeros, so we know that they have 2 sig figs in this number. But what about the 0? Is this 0 right here significant? Well, it's a 0, so rule number 1 doesn't apply here. Rule 2 doesn't apply either because this is not trapped between a non-zero. It is a trailing 0 like rule 3 said, but it only counts if there's a decimal point, and there is no decimal point. So this question right here only has 2 sig figs. Now this middle one right here, 250 point, well, same rules apply to the one that we just did. However, now this one has a decimal point. So look at rule 3 again. Trailing zeros after a non-zero are not significant unless there's a decimal point. This decimal point means that this 0 is not just a placeholder like our first example. It's not saying how big it is. It's saying that we are accurate up until the ones place. We know for a fact that this is a 0, not a 1, not a 2. It's a 0. So this thing has 2 and 5 and 0 as the significant digits. We would say this has 3 sig figs. Now this last problem, you can probably see where I'm going. There's no trapped zeros. We have 2 that are 0, so are these 0 significant? Well, rule 3, trailing zeros, they're both behind non-zeros, and there's a decimal point. So you're going to count all these zeros because we are accurate up until the 10th place. This 2, this 5, this 0, and this 0 are all significant, so this has 4 sig figs. Now the last rule. Leading zeros before a number are not significant. I have an example right here, 0.0025. Notice rules 1 through 3 do not apply to these zeros because these zeros, first of all, are zeros. Number 2, they're not trapped. And 3, they are not trailing behind the 2-5. They are now before it. They are leading. So these are not saying that we are accurate up until the ones place. This is just saying this 25 is really, really small. Okay, so we are going to not count these 3 zeros as significant. This 2 and this 5 are the only significant digits in this, so we say this number has 2 sig figs in it. Okay, so we went over that, took about 8 minutes of our video. Why did we spend so much time on this? Well, when we're multiplying, dividing, that it affects our sig figs because our answer, and if you notice I have a meme to the right, oftentimes you've plugged in during a math class 2 numbers, you multiply them together, and maybe you get a lot more accurate number than you actually started out with. Maybe you start multiplying 2.5 and 3 together, and you got something that was ridiculously long. We're going to find out that not all of these are sig figs. Our answer cannot be more accurate than what we started out with as. So write these down for me. Multiplication and division, you round to the least amount of significant digits. This is because, well, like I said, your answer cannot be more accurate than your least accurate number. So we have 5 times 4.00. We all know that 5 times 4 equals 20, but what should that 20 look like? It should be a 2 and a 0, and then that is it. And actually, let me come out of this so we can get a look at that. So 5 times 4.00, we know that equals 20, but how many sig figs is this supposed to have? You have to look at what you started out with and see how many sig figs these things had. So look at 5, how many sig figs are there? Well, there's only one non-zero, so we have 1 sig fig. 4.00, this 4 we know is a sig fig, so I'm going to put a 1 right here. This 0.00, are these zeros leading or trailing behind the non-zero? They're trailing. And then is there also a decimal point? There is. So these zeros are actually significant. we have 2 more, meaning that this thing really has 3 sig figs. But our answer can only be as accurate as our least accurate thing. So find whatever one was the smallest. In this case, 5 was our smallest one. It only has 1 sig fig, meaning our answer can only have 1. So this we actually would not do anything about, because this 0 is just a placeholder. This would not be counted as significant unless we put a decimal point after it. Okay. Now you can see where we're going with this because the presentation's already showed you what we're headed towards. But when you add and subtract things, you want to round those numbers to the fewest decimal places. So I have an example like here as well. We're going to be subtracting 4 from 5, so let's write that out. 5, I'm going to say minus 4.00, and I like writing them top and bottom in this case because it really helps me keep track of my decimal places. So subtracting these out, we know 5 minus 4 is 1, but how accurate can that be? We'll look at whatever has the fewest amount of decimal places. This 5 right here has 0 decimal places. It doesn't have a decimal at all. Now look at this one right here, 4.00. This one has 2 decimal places. It is as accurate as the hundredth place. Well, look at both of these. This 0 tells you that this is the least accurate number, and so our answer can only be 1, and so we're going to leave it like that. Perfect. Okay, let's bust through this. We'll see how much time we have at the end to do these problems. Okay, so we're going to bust through this real fast, but last unit you learned how to write formulas for salts and molecules. Today we will learn how to calculate how much those formulas of those salts and molecules weigh. And before that, we just need to look at a couple of formulas and make sure we know how many atoms are in it so we can find out how much these things weigh. So look at the top right hand corner, Mg3PO42. This thing has magnesium atoms, phosphorus atoms, and oxygen atoms right here. Take a moment and figure out how many atoms there are of each of these. I'll help you figure out the first one, magnesium. Let's write this down, Mg3PO42. There are, because I see a 3 right here, 3 magnesium atoms. Those 3 Mg atoms. Take a second and find how many phosphorus atoms and oxygen atoms there are. Okay, I don't see a subscript by P, so it looks like there's only one of them, but there are 2 of these phosphate groups. So what you're going to see is there's 2 phosphates, 1 from each group, and then oxygens. There are 4 oxygens in this, but notice there's a 2 outside the parentheses, meaning that we have 2 of those groups. So we actually have a total of 8 oxygen atoms in this. Now I have another example. You'll see it's already on the board. Iron 3 hydroxide. I want you to take a minute and pause. Do that one real quick. You'll notice you'll have to write the formula for this before you can find out how many there are. I'm going to have to bust through this for sake of time, so I'll pause it right now before I write down the answer. So iron is Fe. It has a +3 charge because we have the Roman numeral. Hydroxide is OH minus 1, and in order to have the charges equal 0, you need to have 3 OHs and 1 Fe. So the formula for this looks like FeOH3, meaning we have 1 iron atom, 3 oxygen atoms, and 3 hydrogen atoms. Okay. We're going to bust through this last one super quick for sake of time. So guys, now that we figured out how many atoms are in a formula, we can actually use the atomic mass found on our periodic table to figure out the total mass of one thing. So formula mass and molecular mass, the definition of this is just the mass of one formula of a compound. This is always given in the atomic mass units. So grams, pounds, you use these things to weigh different things. This uses AMU. So guys, the answer to this will be on the slides. I don't have time to go through it too much right here, but what you're going to do is take how many sodium atoms you have, multiply that by the atomic mass, find that on the periodic table, and when you multiply that out, you're going to get a number right here. Then you'll do the same for phosphorus, then you'll do the same for oxygen, Add those together, and then you're going to get the formula mass for formula. Thanks, guys. I'm out of time. Sorry about that.